Look around the room you are in right now. Like, literally just look at the floor beneath your feet or the ceiling above your head, even the chair you're sitting on.
Yeah, just take it all in for a second.
Right. Because we have this, this deep-seated assumption that these things are static. We look at a solid steel beam or a thick concrete pillar, and we just think of it as being completely at rest.
Which is frankly an illusion.
Exactly.
Yeah.
If you could put on a pair of, microscopic physics vision glasses, you would see that absolutely nothing is at rest. Everything around you is locked in this invisible, incredibly violent internal battle.
It's a constant state of war, really.
A silent war, right?
Yeah, a silent, relentless war of resistance. It's fighting against gravity, against atmospheric pressure.
Against the universe quite literally trying to crush or shear or tear these everyday objects apart.
Precisely. The materials around us are only holding their shape because they are actively fighting to do so.
And that's our mission for this deep dive today. We want to make that invisible war visible to you.
We really do.
We're looking at a stack of incredibly detailed engineering materials, mechanics, textbook excerpts, and we're breaking down the fundamental rules that dictate how the physical world holds itself together.
We are going to decode the structural soul of materials.
I love that phrase, the structural soul. So let's unpack this, because right out of the gate, delving into these concepts completely flipped my understanding of a word we use, like every single day.
You mean stress?
Yes, stress. I've always thought of stress as the weight I put on something. If I put a heavy safe on a wooden floor, the weight of the safe is the stress. But that is fundamentally wrong, isn't it?
It is. It's a very common misconception, but yeah, it's fundamentally backward.
So how should we think about it?
Well, if we really want to understand structural mechanics, we have to completely flip the script. Stress is not something that is applied to a material.
Okay.
Stress is developed by the material. Right. The weight of that safe you put on the floor, that is the external load. Stress is the internal resistance that the floorboards create to, push back against that safe.
Oh, wow. Okay.
It is the body's internal microscopic reaction to maintain equilibrium against those external forces.
So it's not the attack, it's the defense.
That is a much better way to look at it, though, I would push that even further. It is a distributed, cooperative defense.
What do you mean by cooperative?
Well, if the floorboards don't develop enough internal stress to perfectly match the external load of the safe, the equilibrium is broken.
Right, the floor just collapses.
Exactly.
Yeah.
So imagine a solid, thick metal bar. Now imagine we hook cables to both ends and start pulling it in opposite directions.
It's a giant tug of war.
Yeah, engineers call this uniaxial loading. We are applying an external force.
Right, I'm picturing the metal bar stuck right in the middle of this tug of war.
Good. Now, in your mind's eye, make an imaginary cut right through the middle of that bar. Just slice it perfectly in half, perpendicular to the way you're pulling.
Okay, sliced.
If you zoom in and look at the cross-section of that cut, you don't just see one massive invisible force arrow holding the two halves together.
Right, because that's not how matter works.
Exactly. Instead, you see thousands, or really millions, billions of tiny atomic bonds, and they're all acting like microscopic springs distributed evenly across the entire surface of that cut.
Ah, so the whole material is pitching in.
Mm-hmm.
Every single atom across that face is just locking arms, holding on for dear life so the bar doesn't snap.
That's a great way to visualize it. And that distribution, that specific intensity of force spread out over the cross-sectional area, that is what engineers define as normal stress.
Normal stress, okay.
Yeah.
And we use the Greek letter sigma for that, right?
Yep, sigma. We care about this distribution because talking about one single internal force doesn't really tell us anything about whether a material will fail.
Why not? Force is force, isn't it?
Think about it this way. A massive amount of total force acting on a 10-foot thick concrete bridge pillar is perfectly fine.
Because the force is spread out.
Yeah, exactly. But that same total amount of force applied to, say, a wooden toothpick.
Oh, yeah. Instant catastrophe. It would just vaporize.
Right. So it isn't the force itself that breaks the material. It is the force per unit area.
That brings up a really interesting translation into the math of it all, I think. Because the fundamental equation is stress equals force divided by area. Sigma equals P over A.
That's the golden rule.
But when we look at how this is actually measured in the real world, the scale of it is just mind-bending. The baseline unit for stress is newtons per meter squared, which is called a Pascal.
Right. Named after Blaise Pascal.
But engineers almost never use a single Pascal, do they? because it's practically nothing.
It really is. What's fascinating here is just how vanishingly small a single Pascal actually is in the physical world.
Give me an example.
Well, a Newton of force is roughly the weight of a medium-sized apple.
Okay, 1 apple.
Now imagine taking the weight of that one apple and spreading it out evenly over a 1 meter by 1 meter square of the floor.
That's a pretty big tile.
Yeah. The stress that apple exerts, distributed over that whole square meter, is 1 Pascal.
Wow. It is literally a wisp of a physical force.
Yeah, if you build a skyscraper to withstand a few pascals of stress, a stiff breeze would just turn it into dust.
That puts it in perspective. So
Yeah.
structural materials are dealing with immense crushing forces.
Precisely. So a single Pascal is totally useless for a civil engineer. They operate in megapascals, or MPa, which is 1 million pascals.
1,000,000 apples.
Yeah, mathematically it translates to a really beautiful intuitive unit. 1 megapascal is exactly 1 Newton of force concentrated onto a single square millimeter.
Oh, that makes so much sense. So imagine that same apple from before, but instead of spreading its weight over a large floor tile, you balance the entire weight of that apple on the head of a tiny pin that is 1 millimeter by 1 millimeter.
Exactly. The stress inside that pinhead is 1 megapascal.
That really brings it into focus. And for things like structural steel, we aren't even talking megapascals, right?
Right.
We jump to gigapascals.
Billions of pascals.
Billions. To use the analogy, that would be like balancing a fleet of heavy pickup trucks on a postage stamp.
That's exactly what it's like. The internal forces holding atoms together are astronomically strong.
Now, earlier you mentioned normal stress. You said the tiny atomic bonds were pulling straight back across our imaginary cut. The term normal here isn't about being like typical or average, is it?
No, not at all. It's a geometric term.
Right.
In mathematics and physics, normal means perpendicular.
Got it.
So the tiny force arrows we imagined inside our cut are pointing straight out, perfectly perpendicular to the flat surface of the cut.
Okay, so when we pull the bar, we stretch it, which develops tensile stress.
Yes. And by convention, engineers treat this stretching as a positive value.
Makes sense. But what if we push on it?
If we push on the ends of the bar, squishing it, the internal arrows flip. They push back outward, still perpendicular to the cut, but they're resisting compression.
So that is compressive stress.
Exactly, and we treat that as a negative value because it's trying to shorten the material.
Okay, so tension and compression are basically the two sides of the normal stress coin. But that leaves a massive blind spot, I feel like, because things don't just stretch and squish in the real world.
No, they don't.
Sometimes they slide.
Mm-hmm.
Which brings us to the other major player in the structural soul, and that is shear stress.
Yes, shear stress.
If normal stress is perpendicular, I'm assuming shear stress is parallel to the cross-section.
You're exactly right. Shear stress, which is denoted by the Greek letter tau, is a tangential force. It acts parallel to the face of the material.
Okay.
It doesn't want to pull the atoms apart or crush them together. It wants to slide them past one another.
So instead of a tug of war, what is the best mental model for this?
Imagine a thick deck of playing cards sitting flat on a table.
Okay, got the cards.
If you place your hand flat on top of the deck and push straight down, your hand is applying a normal compressive force.
And the deck resists, developing normal compressive stress.
Right. But if you keep your hand flat on the top card and slide your hand horizontally, pushing the top of the deck sideways while the bottom stays gripped to the table.
The deck skews.
Exactly. The cards physically slide past one another. That sliding force, acting parallel to the face of each card, is shear stress.
I see. And in a real-world engineering scenario, you see this with fasteners all the time, don't you?
Oh, constantly.
Think of a thick steel bolt holding two massive overlapping steel plates together. If I grab those two plates and try to pull them apart, I'm not stretching the bolt from its head to its nut.
No, you're not.
I am trying to drag the top plate sideways across the bottom plate, and the bolt is caught right in the middle.
It's acting like a pin.
Yeah. The force is trying to slide the top half of the bolt right off the bottom half, like a giant pair of scissors trying to snip it in two.
And the bolt is fighting back with shear stress. That is the perfect example. The bolt's internal atomic structure is resisting being sheared perfectly in half along that parallel plane.
So we have the internal resistance mapped out. Normal stress fights pushing and pulling, and shear stress fights sliding.
Correct.
But, stress is invisible. We can't actually see the atoms fighting. What we can see is the result of that fight.
The visible evidence.
Yes. And that is where the concept of strain comes in. Strain, represented by the Greek letter epsilon, is the geometric consequence of stress. It is the actual physical deformation of the object.
That's right.
But here's where I want to play devil's advocate for a moment.
Okay.
Because this is a concept that historically trips up like a lot of engineering students when they first encounter it.
I think I know where you're going with this.
The rule is that strain is a dimensionless quantity, right? It has no units.
Correct.
But that feels entirely counterintuitive. I mean, if I take a piece of taffy or a rubber band and I stretch it, it gets 2 inches longer. Inches is a physical dimension.
Sure is.
If a steel bridge expands in the summer heat, it might lengthen by several millimeters. Millimeters is a dimension. How can a measurement of physical deformation not have a unit?
This raises a really important question, and it's a vital hurdle to clear if you truly want to understand materials.
Walk me through it.
The reason strain lacks a unit is that it is not a measurement of length.
It's not, no.
It is a measurement of the severity of distortion. The formula for normal strain is the change in length, divided by the original length, delta L over L.
Okay, let's test that.
Let's use your rubber band example. Say you have a rubber band that starts out exactly 10 inches long. You pull it, and it stretches until it is 12 inches long.
So the change in length at delta L is 2 inches.
Right. And the original length is 10 inches. When you divide 2 inches by 10 inches, the inches unit in the numerator and the denominator cancel each other out completely.
Oh.
You are left with a pure mathematical ratio, 0.2.
Ah, I see. It's effectively a percentage. The rubber band is stretched by 20% of its original size.
Precisely. And that pure ratio tells an engineer infinitely more about the danger the material is in than a raw unit of length ever could.
Why is that?
Well, if I come to you and say, hey, I have a structure, and it just stretched by 2 inches, you have no idea if that is catastrophic or irrelevant.
I guess that's true.
If a massive 2-mile-long suspension bridge stretches by 2 inches under the weight of traffic, that strain is microscopically close to zero. The bridge is perfectly safe.
Right.
But if a 4-inch steel bolt holding a crane together stretches by 2 inches...
Oh. Then the strain is 0.5 or 50%?
Exactly. That bolt has catastrophically failed, and the crane is probably collapsing as we speak. The absolute length doesn't matter. The severity of the stretch relative to its starting state is what matters. That is what strain is.
That elegantly solves the unit problem. Makes total sense now. It's a universal ratio of distortion.
Yep.
And logically, just as we have normal stress and shear stress, we have normal strain and shear strain. Normal strain is what we just described, getting longer or shorter. But what is shear strain? We can't use length for sliding.
We go back to your deck of cards. When you slid your hand across the top, the deck didn't get notably taller or shorter. Normal strain didn't really occur, but it profoundly changed shape.
Right. What started as a perfectly upright rectangular block skewed into a slanted parallelogram.
Think about the internal angles of that deck. Before you pushed, every corner was a perfect 90-degree right angle. After you pushed, the corners became acute and obtuse. Shear strain, which is denoted by the Greek letter gamma, measures exactly that, angular distortion.
So it's measuring angles.
Yes. It is the measure of how much those internal angles have skewed away from a perfect 90 degrees.
So normal strain changes the size of a material, and shear strain changes the shape of a material.
You nailed it.
This is brilliant because it means we have completely defined the battlefield here. We know the internal forces, which is stress, and we know the geometric consequences, which is strain.
But every material fights this war differently.
Exactly. If I apply the exact same stress to a block of rubber and a block of steel, the rubber is going to show massive strain, and the steel will show almost zero.
It won't even flinch.
Which naturally leads us to ask, how do we define a specific material's unique battle strategy?
We have to decode its DNA, and we do that by mapping how its stress relates to its strain.
Right, which brings us to a really fundamental law of physics, Hooke's law.
Good old Hooke's law.
Discovered by the 17th century polymath Robert Hooke. The law is beautifully simple. It states that for a solid material, stress is directly proportional to strain, as long as the force isn't too extreme.
It is the absolute bedrock of linear elasticity. If you pull a spring with 1 unit of force, it stretches 1 inch. If you pull it with 2 units of force, it stretches 2 inches, 10 units, 10 inches.
It's perfectly linear.
The deformation is perfectly mathematically linear.
But the secret sauce is what that proportion is for different elements of the physical world. The exact ratio between stress and strain is a material's unique fingerprint, right?
Exactly. Engineers call these ratios the Moduli matrix, or the 3 elastic constants.
Let's break these down, because they define exactly how a material experiences the universe. First up is Young's modulus, denoted by the letter E.
Young's modulus is the ratio of normal stress to normal strain. In practical terms, it represents a material's inherent absolute stiffness.
Absolute stiffness.
Yes, it is the measure of how fiercely a material fights back against being lengthened or shortened.
So a high E value means the material demands a massive Herculean amount of stress to yield even a microscopic fraction of strain.
Right. Structural steel has an enormous Young's modulus. You can literally park cars on it, and it barely compresses a millimeter.
While rubber, on the other hand, has a tiny Young's modulus, a child can pull it and generate massive strain.
Exactly. Young's modulus dictates the primary axial stiffness. But, materials face more than just straight pulling.
Which brings us to sliding again.
Right. That is where the second constant comes in, the shear modulus, denoted by G. This is the ratio of shear stress to shear strain.
So if Young's modulus is about resisting changes in length, the shear modulus is about resisting changes in shape. It's the angular stiffness.
Precisely. Think of a cube of gelatin versus a cube of dense oak wood.
Okay, gelatin and wood.
If you lightly push sideways on the top of the gelatin, it immediately wiggles and skews into a slanted parallelogram. It offers very little resistance to angular distortion.
So it has a very low shear modulus.
Exactly. But if you push sideways on the cube of wood, it remains a rigid, perfect cube. It requires an immense shear force to distort its internal angles. High shear modulus.
Okay, length and shape, that covers almost everything we experience on dry land. But the third constant, the bulk modulus, denoted by K, requires a totally different mental model, I think.
It does.
It is the ratio of direct, uniform pressure to volumetric strain. I found this one truly fascinating.
The bulk modulus requires us to step away from simple tug-of-wars or sliding cards. Imagine taking a solid sphere of a material, let's say a solid sphere of aluminum, and dropping it deep into the ocean.
Like all the way down into the Mariana Trench.
Yeah, as deep as it goes.
Down there, it is subjected to immense hydrostatic pressure. But the force isn't pulling it, and it isn't sliding across it. It is squeezing the sphere equally from every single possible direction at once.
Exactly. Under perfectly uniform omnidirectional stress, the sphere isn't going to stretch into an oval, and it isn't going to skew into a diamond shape.
What happens to it?
It is going to experience a change in volume. The immense pressure will force the atoms closer together, and the sphere will remain a perfect sphere, just a slightly smaller one.
Wow.
The bulk modulus, K, measures the material's ultimate resistance to that volumetric crushing. A high K means the material is incredibly stubborn about giving up its volume, even under apocalyptic pressure.
So we have E for absolute stiffness, G for shape rigidity, and K for volume preservation, the holy trinity of material DNA.
That's a great way to put it.
If you know these three numbers, you essentially know the soul of the material. But here's where it gets really interesting, and where the physical world just refuses to let things be simple.
Oh, physics never lets things be simple.
The reality is, these dimensions do not operate independently. A pull in one direction has inevitable consequences in the others. I want to explore this transverse effect.
Yeah, this is where intuition often fails us, but the math reveals the truth of the universe.
Let's go back to stretching our rubber band. We established that pulling it causes normal strain. It gets longer.
Right.
But anyone who has ever played with a rubber band knows that as it gets longer, it simultaneously gets noticeably thinner.
It does.
Why? Why does a one-dimensional pull along the length force a consequence in the thickness and width? Why can't the material just get longer and stay the exact same thickness?
If we connect this to the bigger picture of physics, it really comes down to the conservation of a material's internal state. You are not magically manifesting new rubber molecules out of thin air when you pull the band.
Right, the total amount of matter you have is fixed.
So to accommodate the drastic new lengths you are forcing upon it, the material has to draw resources from its other dimensions. It shrinks laterally transversely to compensate for the axial stretching.
It's essentially robbing Peter to pay Paul. The length steals from the width.
That is a brilliant analogy. And this unavoidable secondary shrinking is governed by another critical structural constant, which is Poisson's ratio.
Denoted by the Greek letters mu or nu.
Right. Named after Simeon Denis Poisson, a brilliant French mathematician who formalized this transverse relationship in the early 19th century.
Let's unpack the mathematics of Poisson's ratio, because there is a specific quirk in the formula that I want to dissect. The formula is mu equals the negative of the lateral strain divided by the axial strain. Why is there a mandatory negative sign hard-coded into the front of this equation? It seems really odd to force a negative into a core constant.
It might seem odd at first glance, but that negative sign is actually a profound mathematical proof of the exact robbing Peter to pay Paul reality you just described.
Let's walk through it.
Okay, say you pull the rubber band, that is tension. By engineering convention, tension is positive, so the axial strain, the lengthening in the denominator, is a positive number.
Okay, following so far.
Now, because the material is stretching axially, we know from physical observation that it must be thinning laterally. Thinning is a reduction in dimension, which means it is compression.
And by convention, compression is a negative strain.
Exactly. So your numerator, the lateral strain, is a negative number.
Right. And if you divide a negative numerator by a positive denominator, basic algebra dictates the result is a negative number.
Exactly. But Poisson and the engineers who followed wanted this ratio to be a positive absolute constant for natural materials.
So they just artificially flicked it.
Basically, they deliberately placed a negative sign at the very front of the equation. That leading negative multiplied by the negative result of the division cancels out into a positive. What this does mathematically is bind the physical reality into law. It proves that tension in one direction absolutely, inevitably mandates compression in the transverse direction.
But if you stretch it, it must shrink laterally.
And if you squish it down, it must bulge outward. The math forces the physical reality.
The elegance of that is just stunning. The math simply doesn't allow a material to gain dimension in all directions simultaneously under a uniaxial load.
It can't.
And materials vary wildly in how severely they obey this transverse effect. The documentation provides a fascinating scale called the Poisson spectrum, which ranges from 0 to 0.5 for naturally occurring materials.
It's a really revealing spectrum.
Let's walk the spectrum because the practical applications are amazing. Let's start at the absolute bottom, a Poisson's ratio of essentially 0.
A ratio of 0 means there is no transverse effect whatsoever. If you compress the material along its axis, it does not bulge outwards laterally at all.
Not even a millimeter.
Not at all. And the primary example of this in nature is cork.
Which perfectly explains why we have used cork to seal wine bottles for centuries. I had never considered the mechanics of this.
Most people don't.
When you use a mechanical press to force a cork down into the narrow glass neck of a wine bottle, you are applying intense compressive stress.
Very intense.
If you tried to do that with a rubber stopper, which bulges violently outward when you compress it vertically, the lateral expansion would exert so much outward pressure that it would instantly shatter the glass neck of the bottle.
Exactly. But cork has a Poisson's ratio of 0. As you squish it downward, its width stays perfectly constant. It absorbs the compression internally without pushing outward against the fragile glass. It is nature's perfect bottle stopper, entirely because of its unique lack of a transverse effect. It's a wonderful example of humans intuitively utilizing complex structural mechanics long before we had the math to describe it.
Moving slightly up the spectrum, we hit the 0.2 to 0.27 range. This is known as the brittle zone, encompassing materials like cast iron and concrete.
These materials do have a transverse effect, but it is relatively subdued. If you compress a concrete pillar, it will try to bulge slightly in the middle, but not dramatically.
However, this zone is characterized by a lack of forgiveness, which we will touch on later.
Oh yeah, we'll get to that.
Then we enter the 0.25 to 0.33 range. This is the Goldilocks zone for modern civilization. Structural steel, aluminum, titanium, almost all the metals we use to build our world live in this narrow band.
Yep. If you stretch a steel beam, it will thin out laterally by roughly 30% of the proportional amount it stretches.
Which provides a highly predictable, reliable deformation profile for structural engineers. It behaves exactly how we want it to.
Precisely.
And then we reach the absolute maximum ceiling for natural materials, 0.5. Rubber sits right at this limit.
Rubber is a fascinating boundary case in physics because a Poisson's ratio of exactly 0.5 mathematically means the material is perfectly incompressible.
Wait, I have to stop you there. What do you mean incompressible? I can squeeze a rubber ball in my hand right now. I can physically compress it.
I wouldn't quite phrase it that way. Consider the difference between shape and volume.
Okay.
When you squeeze that rubber ball in your hand, you are absolutely changing its shape. You are distorting it, but you are not changing its volume. Really, if you start with exactly 1 cubic inch of rubber and you stretch it, twist it, or squish it, it will warp and thin out in exact, perfect mathematical compensation so that its total volume remains exactly 1 cubic
Right.
inch.
Remember the bulk modulus we discussed earlier, the resistance to volume change?
Exactly. For a material with a Poisson's ratio of 0.5, that bulk modulus is theoretically infinite. The material will furiously refuse to be packed into a smaller volume. It'll always bulge perfectly to escape the pressure.
So rubber is the absolute limit of natural physics at point 0.5, and cork is the floor at 0. But in exploring these limits, we uncover something that sounds like absolute science fiction.
You're talking about the negative side.
Yes, there is a category of materials where Poisson's ratio is less than 0, a negative mu. They're called synthetic auxetics.
They're wild.
If the ratio is negative, that means the math reverses. If you pull it, it doesn't get thinner, it gets thicker laterally. It expands.
I know it completely defies every intuition we have about how physical objects should behave in our hands, but auxetic materials are very real.
How is that even physically possible without breaking the laws of conservation? If I stretch a rubber band, it thins. If I pull an auxetic material, it swells up like a pufferfish. Where's the extra width coming from?
It doesn't come from new material, it comes from microscopic geometric unfolding. You have to look at the cellular structure.
Walk me through it.
Most materials are packed somewhat solidly, but imagine a material whose internal structure looks like a honeycomb, but instead of regular hexagons, the hinges of the hexagons are folded inwards on themselves.
Think of the shape of a crumpled, collapsed bow tie.
That's exactly it.
Okay, I'm picturing a dense web of these collapsed little bow ties.
When you apply axial tension, when you pull on the ends of that structure, you are physically pulling the ends of those bow ties. What happens?
The inward folded hinges are forced to pop outward and straighten.
Yes. The mechanical unfolding of millions of these microscopic hinges forces the entire macrostructure to expand sideways. It's essentially deploying stored geometric width.
That is mind-blowing. It's structural magic disguised as geometry. But why would we ever need a material that gets fatter when you pull on it? What is the practical application of this bizarre property?
The applications are revolutionary, particularly in impact absorption. Think about advanced body armor, like a bulletproof vest.
Yeah?
When a high-velocity projectile strikes standard Kevlar, the fabric stretches inward, and as we know, stretching makes standard materials thinner right at the point of impact.
Which is exactly where you need the most protection.
Right. But if the vest is woven with an auxetic material...
When the bullet hits and forcefully stretches the fabric inward, the lateral expansion kicks in.
Exactly. The material around the impact zone will rapidly expand and thicken, essentially rushing density toward the point of attack to catch the bullet.
The harder it is stretched by the impact, the thicker and denser the shield becomes at the focal point. That is incredible.
We also see this in advanced medical stents that expand uniformly and to keep arteries open, or high-performance running shoes that thicken laterally when the sole is stretched upon foot strike, providing dynamic cushioning.
It's just a brilliant manipulation of the rules.
Yeah?
And speaking of rules, what is truly elegant about structural mechanics is how inescapably linked these properties are.
Everything is connected.
You don't just have Young's modulus E, shear modulus G, bulk modulus K, and Poisson's ratio mu floating around independently. The math binds them all together in a harmony of equations.
It does.
For instance, Young's modulus equals 2 times the shear modulus multiplied by 1 plus Poisson's ratio. E equals 2G times 1 plus mu.
And similarly, E also equals 3K times 1 minus 2 mu. This mathematical interlinking is the greatest triumph of linear elasticity.
What does that mean for a working engineer?
What it means is that an engineer does not need to run 100 different complicated tests to understand how a new titanium alloy will behave in every conceivable scenario. Nope. If you can simply measure its absolute stiffness, E, by pulling on it, and measure its transverse thinning, which is Poisson's ratio, you instantly possess its complete structural DNA.
So using those equations, you can mathematically deduce exactly how it will resist shear tearing or exactly how it will respond to deep ocean-crushing pressure.
Exactly. The structural soul is an open book, provided you can read the math.
So we know the DNA, but how does this DNA dictate the actual lifespan of a material under duress? How does a piece of steel live, fight, and ultimately die?
To understand this, engineers subject materials to a crucible known as the tensile test.
Walk us through this experience.
The tensile test is the gold standard for uncovering a material's narrative. It is brutally simple, but incredibly revealing. You take a standard machine specimen of a material, let's use mild steel, the backbone of modern construction.
Yeah.
The specimen looks a bit like a thick metal dog bone. You clamp the top end into a stationary grip and the bottom end into the massive hydraulic jaws of a universal testing machine. And then you turn the machine on.
And the hydraulic jaws just slowly, inexorably start pulling downward. A pure, unstoppable uniaxial force.
Yes. And as it pulls, the machine's computers plot a real-time graph. On the y-axis, going up, is stress, the internal resistance the steel is developing to fight the machine.
And on the x-axis, going right, is the physical stretching the machine is inflicting on the steel.
Exactly. The resulting line drawn on this graph is literally the biography of that specific piece of metal. Let's trace the milestones of its life.
The journey begins at the origin. 0 stress and 0 strain. The machine starts pulling. We enter the first major chapter, the elastic region.
As soon as the force is applied, the steel fights back ferociously. The line on the graph shoots upwards at a steep, perfectly straight diagonal angle.
Just a straight line up?
In this initial phase, Hooke's law reigns supreme. The relationship between the stress developed and the strain experienced is perfectly linear.
And the slope of that straight line, that
Yeah.
incredibly steep angle, that is literally Young's modulus visualized, right? The steeper the line, the stiffer the material.
Precisely. The steel is acting exactly like a very stiff spring. This linear perfection continues up to a point known as the proportionality limit, and then just slightly further to the elastic limit.
And this entire initial zone is defined by one beautiful, vital word for engineers: recovery.
Right, because if you hit the kill switch on the hydraulic machine anywhere in this zone and release the clamps, what happens?
The steel bar will instantaneously snap back to its exact original microscopic dimensions.
0 permanent damage. Complete geometric recovery. The atoms stretched apart, but the bonds never broke.
This is the safe zone. This is where civil engineers want their bridges and skyscrapers to live their entire lives, bending in the wind, stretching under the weight of a train, but always, always returning to 0.
But the hydraulic machine doesn't stop. It keeps pulling.
Right. We cross the elastic limit and cross the point of no return into the next chapter, the yield point. The material stops acting like a perfect spring. What does yielding actually look like, both on the graph and in the physical metal?
On the graph, it is a dramatic shift. The steep, straight line abruptly curves over and becomes almost horizontal.
Oh.
The machine continues to pull, forcing more and more strain, stretching it rapidly. But the stress on the y-axis barely goes up. In fact, it might even drop slightly. The material is surrendering.
It's giving up the fight.
At a microscopic level, yes. It is no longer developing massive internal resistance to match the stretch. The internal atomic bonds are finally being overwhelmed.
What's actually happening to the atoms?
The crystalline lattice of the steel is shearing. Entire planes of atoms are slipping past one another. The deformation is no longer a temporary stretch. It is permanent structural warping. If you stop the machine now, the bar will be permanently longer.
This brings up an incredibly important dichotomy in materials: ductility versus brittleness.
Oh, this is crucial.
A ductile material, like the mild steel we are testing, or gold or copper, has a long, drawn-out yield phase. It will stretch, warp, and visibly deform significantly while surrendering before it ever actually snaps.
Yeah.
But a brittle material, like glass, cast iron, or pure concrete, has almost no yield phase whatsoever. It stays perfectly elastic, fighting hard, right up until the moment it violently, explosively shatters.
And this is exactly why engineers vastly prefer ductile materials for human structures. You want a building's skeleton to yield before it fails.
Right, because yielding provides a warning. If a massive earthquake overloads a ductile steel frame, the beams will visibly sag, bend, and warp. The building might be ruined, but it stays standing long enough for people to evacuate.
Exactly.
If we built skyscrapers out of massive brittle glass pillars, they would look pristine during the earthquake right up until the millisecond they explosively pulverized, crushing everyone inside. Ductility is structural forgiveness.
That is a perfect way to phrase it. Structural forgiveness. But let's return to our yielding steel bar in the machine. It is slipping. It is permanently deforming. We have entered the region of plasticity.
Okay, so the metal is ruined.
But the steel isn't dead yet. In fact, as the machine keeps pulling, the line on the graph starts to curve upwards again. Yeah, the material begins developing more stress. It starts fighting back harder than ever.
This makes no sense at first glance. If the atomic bonds are slipping and the material is constantly damaged, why is it suddenly getting stronger?
It is one of the most remarkable defense mechanisms in physical science. It is called strain hardening.
Strain hardened.
Yes, the crystal lattice planes are slipping and sliding, but as they slide, it isn't a smooth process. Microscopic defects in the metal, called dislocations, start crashing into each other. They tangle up, they create roadblocks for other slipping planes.
It's like a massive traffic jam occurring inside the molecular structure of the metal. The more the planes try to slide, the more congested and locked up they become.
Exactly. The material is fundamentally reorganizing its internal structure, packing itself into a denser, highly tangled configuration specifically optimized to resist the exact direction you are pulling it.
That's wild.
Because of this tangled internal traffic jam, the material forces the hydraulic machine to work harder. The stress required to keep pulling climbs higher and higher until it reaches the absolute apex of the curve, the ultimate tensile stress.
That is the absolute maximum strength the material can ever muster.
Yes.
The dying star burning its brightest just before the end. Because after that ultimate peak, we enter the final, fatal chapter, necking and fracture. The curve on the graph begins to droop downward.
It does.
The stress is dropping, the strain keeps stretching rightward, and eventually, SNAP, the bar violently breaks in two. But this sequence introduces a massive, common misconception that we need to clear up. I want to play devil's advocate and look at this mathematically.
Go right ahead.
On the standard engineering graph we just plotted, the line visibly drops downward after the ultimate peak right before the break. The stress on the y-axis goes down.
Right.
It looks, to anyone reading the graph, like the material is weakening, getting softer, and giving up right before it snaps. Does the material actually get weaker in its final moments?
This is perhaps the single most misunderstood element of structural mechanics. The answer is absolutely emphatically no. The material never gets weaker.
So why does the graph show it dropping?
The confusion arises because the standard graph is plotting what we call engineering stress, which contains, basically a mathematical lie of omission.
Okay, what is the lie? Why does the engineering curve drop if the material isn't getting weaker?
It comes back to the core equation. Stress equals force divided by area. When engineers generate that standard curve, they calculate the area in the denominator using the original untouched cross-sectional area of the dog bone before the test even started.
That's a constant, easy number to use.
Right. But what is physically happening to the shape of the bar as it approaches failure?
If you watch a video of a tensile test, it's obvious. After the ultimate peak, the stretching doesn't happen evenly across the whole bar anymore. It focuses on one weak spot in the middle, and the metal visibly violently thins out.
Like pulling warm taffy.
Yeah, it forms a narrow, stretched neck. This is called necking.
Exactly. The actual physical cross-sectional area in that necking region is shrinking rapidly. The denominator in our equation is not a constant, it is plummeting.
I see it now. If the mathematical denominator, the area, is getting smaller and smaller, the resulting fraction, the stress, must be getting larger and larger.
Yes. If you ignore the original area and you calculate the force divided by the instantaneous area, the actual tiny neck-down thickness of the metal at that exact millisecond, you generate a totally different curve.
The true stress curve.
Exactly. And if you look at the true stress curve, it never drops. It shoots straight up, curving aggressively higher and higher. The material is strain hardening relentlessly, fighting with exponentially increasing ferocity, right up until the very microsecond its atomic bonds are literally ripped apart.
The material goes down swinging, it never surrenders. So the engineering graph just makes it look like it weakens because we're using a lazy original area calculation.
Basically, yeah.
But that begs the question. Why do engineers use the engineering stress curve at all? Why use a graph that visually misrepresents the material's strength at the end of its life?
Because engineering is ultimately about practical reality, not just theoretical physics.
How so?
Think about the context. If you are an engineer designing a skyscraper and a steel beam in your framework has passed its yield point, permanently deformed, reached its ultimate stress, and has necked down to half its original thickness. You do not care what its true stress is right before it snaps. The beam has already catastrophically failed its structural purpose. The building is already condemned.
Oh, I get it. We designed the world to operate exclusively in the elastic region, where the original area and the true area are virtually identical.
Exactly. The engineering curve is perfectly accurate in the safe zone, and it is vastly simpler to calculate.
That perfectly frames the divide between the physicist and the engineer. The true curve is the violent physical reality. The engineering curve is the practical boundary of human safety.
Couldn't have said it better.
So we have tracked the life cycle of force and deformation. But to truly understand how structures survive the real world, we have to shift our perspective from force to energy. And that brings us to the concept of the material battery: strain, energy, and impact.
This is a crucial pivot. We are moving from static loads to dynamic reality.
The documentation introduces a profound concept called resilience. To visualize this, it tells us to look at the stress-strain graph we just built, specifically looking only at that first chapter, the straight line of the elastic region.
Right.
If you mathematically calculate the area under that straight diagonal line, you get a geometric triangle. That shaded triangular area represents resilience, which is defined as the strain energy stored per unit volume.
The battery analogy you hinted at is the most accurate way to understand this. A piece of structural steel is a massive, incredibly stiff, rechargeable battery. Yeah. When you apply a load to it, say driving a heavy truck onto a bridge, you are doing work on the steel. You are pumping kinetic energy into the material. The atoms stretch apart, and in doing so, they store that energy. The material is charged with strain energy.
And because we are in the elastic region, when the truck drives off the bridge, the load is removed. The steel snaps back to its original shape. It discharges. It releases all that stored strain energy back out.
Precisely.
Yeah.
And the mathematics match the geometry on the graph perfectly. How do you find the area of a right triangle?
It is 1/2 multiplied by the base, multiplied by the height.
Right. On our graph, the base is the strain, epsilon, and the height is the stress, sigma. So the stored energy per unit volume is 1/2 times stress times strain.
And if we use Hooke's law to substitute strain out of the equation, we get a beautiful formula. Stress squared divided by 2 times Young's modulus, sigma squared over 2e.
It's an elegant formula.
And if we calculate that exact formula right at the yield point, the absolute limit before permanent damage occurs, we find the modulus of resilience. That represents the maximum possible charge the material battery can hold before it warps, and the battery is permanently ruined.
Right. But remember, that formula is just for a tiny unit volume. If we want to know the total strain energy capacity for an entire physical object, which engineers denote with the letter U, we have to multiply it across the object's geometry.
And the full formula is U equals the load squared times the length divided by 2 times the area times Young's modulus, P squared L over 2AE.
It is a vital formula because it proves that energy capacity isn't just about the material, the E value. It is heavily dictated by the physical geometry, length, and area.
Let's conceptualize this without getting bogged down in reading raw scientific notation. Let's say you have a standard solid steel bar about the size of a baseball bat, and you hang a massive weight from it, say the weight of 3 heavy pickup trucks. Using the math, you calculate the total strain energy stored in that stretched steel bat, and it comes out to roughly 30 joules.
Okay, 30 joules of total stored strain energy.
Here is my question. Why do we care? If the bat is just hanging there statically, holding up the 3 pickup trucks without yielding, why do engineers obsess over calculating those 30 joules?
Because the real world is rarely static. Engineers care deeply about joules because they have to design for impact loads.
An impact load, a dynamic, sudden, violent strike.
Yes. If you gently, slowly lower the weight of 3 pickup trucks onto that steel bat, the load is applied gradually, the stress builds slowly, and it handles it easily.
Right.
But what if that exact same amount of force doesn't come on slowly? What if it arrives in the form of a speeding car slamming into a highway safety barrier?
Or a massive, multi-ton drop hammer malfunctioning and slamming down in a factory?
Exactly. That is kinetic energy moving at high velocity. The structure cannot just statically resist it. It must act as a battery and instantaneously absorb all the kinetic energy of that strike.
And it has to absorb all those joules of kinetic energy without its internal charge exceeding its modulus of resilience. Because if it absorbs too much energy, it crosses the yield point and the barrier permanently deforms or snaps.
Exactly. If the kinetic energy of a crashing car delivers 100 joules of energy in a millisecond, but the steel barrier beams can only store 30 joules elastically.
The math dictates failure.
The remaining 70 joules of energy cannot just vanish. It must go somewhere. So it is forcefully diverted into tearing, ripping, and permanently realigning the crystal lattice of the steel. The barrier yields, crumples, or breaks.
This absolutely perfectly explains the evolution of car bumpers. I've always wondered about this. If you look at an old vintage car from the 1950s, they had these massive, rigid, heavy chrome bumpers.
Oh, they were incredibly stiff. A very high Young's modulus.
But because they were so stiff and didn't deform, they had a very small capacity to store strain energy elastically. So in a crash, the bumper didn't absorb the joules of the impact.
Where did the energy go?
The energy bypassed the rigid bumper and transferred directly into the frame of the car and, tragically, into the fragile passengers.
Yes, the classic rigid bumper was terrible at managing strain energy. Modern car engineering completely flipped the paradigm.
They introduced crumple zones.
Exactly. The front structure is designed specifically with geometry and materials intended to massively yield and permanently deform during a crash.
They're designed to fail.
They are engineered to sacrifice themselves to absorb massive amounts of joules through controlled plastic yielding. Tearing metal takes an immense amount of energy. By forcing the structure to crumple, it aggressively drains the kinetic energy out of the crash before that energy can reach the passenger cabin. It uses plasticity to empty the energy battery.
That is profound. Or, to look at it from the elastic side, look at a steel suspension spring in a car. A spring is a masterclass in manipulating geometry to maximize the battery capacity.
By taking a long steel rod and coiling it up, you massively increase the length variable in our energy equation within a compact space.
This creates a massive capacity to store strain energy elastically without ever yielding. When you hit a pothole, the string violently compresses, absorbs hundreds of joules of shock instantly, stores it safely in the atomic bonds, and then smoothly releases it as it bounces back.
Or consider fluid dynamics in heavy industry. The documentation mentions pipelines surging with pressure.
Or a water hammer.
Yes. If a massive valve on an oil pipeline suddenly slams shut, the momentum of thousands of gallons of moving fluid violently halts. It creates a massive hydraulic shockwave.
So the pipe acts as a battery.
The steel pipe must have the sheer resilience to act as a battery, absorbing that sudden massive spike in joules by expanding slightly outward, safely within its elastic limit, rather than fracturing and causing a catastrophic environmental spill.
The material battery is the unsung hero of everyday safety. It is the structural soul actively protecting us from the chaos of dynamic physics.
But the battery has a weakness. And that brings us to the final frontier of structural mechanics.
What's the weakness?
We have talked about surviving one massive violent impact, but what happens when a structure is subjected to a million tiny impacts?
That introduces the silent killer, fatigue life. Let's explore this, because earlier we established a rule that seems to have an exception. We said that if you load the material within the elastic region, it charges the battery, and when you let go, it discharges perfectly, returning to exactly zero, complete recovery.
In a perfect, theoretical, frictionless universe, yes, it is a 100% efficient transfer. But reality is never perfect.
What happens in reality?
At the microscopic atomic level, there are always impurities, minor grain boundary defects, and internal friction, which means that every single time a load is applied and removed, even a tiny load perfectly within the safe elastic limit, a microscopic fraction of that strain energy is not released.
The battery doesn't fully discharge.
Exactly. A tiny amount of energy is absorbed by the material as internal friction. This absorbed energy manifests as microscopic, localized plastic deformation. Tiny atomic-level slip planes occur around impurities.
So the battery is slowly, invisibly degrading with every single use.
Yes. If the load is very light, the energy absorption per cycle is minuscule, and the structure has a long, practically infinite fatigue life. It can be cycled millions of times.
But if the load is heavier?
Even if it is still well below the yield point, the energy absorbed per cycle is higher. Those microscopic slips accumulate. They join together into microcracks.
And eventually,
after thousands of repeated cycles, those cracks propagate, and the material will suddenly catastrophically snap with almost no warning, even under a normal everyday load.
This is exactly why a paperclip snaps. If you take a metal paperclip and bend it slightly, it springs back. But if you intentionally bend it back and forth 90 degrees, you are not exceeding its ultimate tensile strength with your bare fingers.
But you are pumping so much energy into the hinge point with every cycle that the localized fatigue accumulates rapidly. The microcracks form, the metal heats up from the internal friction, and within 10 bends, it snaps in half. It is the exact same mechanism, scaled down. And historically, ignoring fatigue life has led to some of those catastrophic failures in engineering history. Consider the Liberty ships of World War II.
The cargo ships, what happened to them?
They were mass-produced to carry supplies across the Atlantic. To build them incredibly fast, they used novel welding techniques instead of traditional riveting.
Okay, that sounds efficient.
But they didn't fully understand the fatigue concentrations those continuous welds created, especially in the freezing, violent, cyclical swells of the North Atlantic Ocean.
The constant repetitive hogging and sagging of the ships over massive waves acted just like your fingers bending the paperclip.
Yes. Micro cracks formed at the square corners of the cargo hatches. And because the steel became brittle in the freezing water, those cracks propagated at the speed of sound. Several of these massive 400-foot steel ships literally snapped clean in half right in the middle of the ocean, under loads they should theoretically have been able to handle statically. It was a brutal lesson in fatigue and dynamic loading.
That is terrifying.
Yeah.
It proves that you can't just design for the heaviest possible weight.
Yeah.
You have to design for the rhythm of the environment. Okay, let me play devil's advocate one last time to synthesize all of this.
Go for it.
Let's say I am a master engineer. I design a steel column for a new building. I calculate the static stress to ensure it is way under the ultimate limit. I calculate the battery capacity to ensure it can absorb any accidental impact without yielding. And I calculate the fatigue life so it won't snap from cyclical wind loads. I have perfectly protected the material. My building is unequivocally 100% safe, right?
Not necessarily. You have perfectly protected the material, but you have not guaranteed the stability of the structure.
Wait, what is the difference? If the material doesn't break, how can the structure fail?
The difference is a terrifying phenomenon called buckling. We have entered the stability frontier. To understand this, let's step away from steel and imagine a cheap, flexible plastic ruler, the kind you used in elementary school.
Okay, I have it in my head.
If you hold both ends of that plastic ruler and pull outward in tension, it is remarkably strong. It's very hard to snap a ruler by pulling it, but if you put one end on the desk, put your hand on the top, and push straight down, compressing it like a column, what happens?
Long before the plastic itself actually crushes or yields, the entire ruler suddenly bows violently outward in the middle. It whips sideways into a C shape.
Yes, that is buckling. It is a failure of macroscopic instability, not a failure of microscopic material strength.
So the plastic itself was fine.
The plastic itself was perfectly fine. It never reached its compressive stress limit, but the shape of the column became dynamically unstable. The internal strain energy found it easier to escape by bending the geometry laterally rather than compressing the atoms axially.
So a column in a building could be made of the strongest, most expensive gigapascal titanium alloy in the world, with a massive capacity for stress. But if the architect designs the column to be too tall and incredibly thin, it doesn't matter how strong the metal is.
Exactly. It will buckle and collapse under a fraction of its true material capacity. The material will be barely breaking a sweat while the geometry fails spectacularly. The most famous example of this kind of dynamic instability, though driven by aeroelastic flutter rather than pure compression, is the Tacoma Narrows Bridge collapse in 1940.
The famous black and white footage of the bridge twisting in the wind.
Yes, galloping Gertie. The wind blowing across the bridge didn't exceed the tensile strength of the steel cables. But the aerodynamic forces began feeding kinetic energy into the structure in a harmonic rhythm.
And it buckled.
The strain energy accumulated, the geometry became unstable, and the massive concrete and steel roadway began twisting and heaving violently, buckling and tearing itself apart. It was a failure of stability, not just raw strength.
The documentation mentions advanced mathematical tools used to predict this, like Castigliano's theorem and energy methods.
Because predicting buckling in complex structures is incredibly difficult. It involves analyzing exactly how the strain energy is distributed through every centimeter of a column's geometry.
How do they do that?
Engineers use these complex energy methods to calculate something called the critical load. This is the exact mathematical threshold, the tipping point, where a structure will suddenly stop compressing elastically and instead instantly bow outward and collapse.
So structural engineering is an impossibly delicate balancing act. You have to satisfy the microscopic limits of the material, managing the stress, strain, and fatigue life. And you have to simultaneously satisfy the macroscopic geometric limits of stability, ensuring the critical load is never reached.
It requires visualizing the building not just as a shape, but as a living network of flowing forces and stored energy.
Which perfectly sets up our final synthesis for this deep dive. We have essentially mapped out the mental workflow that engineers use to keep modern civilization standing. Step 1. Identify the attack. Are we pulling or are we sliding?
Axial or shear loading.
Right. Step 2. Deploy the correct defense by looking at the material's DNA, the moduli matrix. Are we relying on Young's modulus for stiffness, shear modulus for shape retention, or bulk modulus for volume?
Yeah, exactly.
Step 3. Plot the battle on the stress-strain curve to ensure the structure stays safely in the elastic recovery zone, far away from permanent plastic yielding.
Yep, stay in the safe zone.
And step 4. Check the energy battery. Ensure it has the capacity to absorb the joules of a sudden impact, and verify that the geometry is thick enough to remain stable against the sudden lateral collapse of buckling.
When you put all that together, you realize that the skyscrapers, bridges, and homes around us aren't just passively standing there. They are highly active entities. They're constantly internally pushing back against the weight of the universe.
Which brings me right back to where we started this entire conversation. I asked you to look at the room around you, the floor, the ceiling, the walls. Knowing what we know now about the invisible mechanics of the world, the structural soul, I want to leave you with a provocative final thought that builds on everything we've explored today.
What's the thought?
We talked about fatigue and how every single cycle of load being applied and removed involves a tiny, imperfect transfer of strain energy. We talked about plastic deformation and how yielding causes a permanent microscopic traffic jam and realignment of the crystalline lattice inside the metal.
The material physically, irrevocably changes itself to survive the stress it experiences.
Exactly, which implies something deeply profound. The concept of material memory. Think about it. The structural materials around us, the massive steel beams of the bridges we drive over every day, the aluminum frames of the airplanes we fly in, the concrete pillars buried deep in our basements, they're essentially physical ledgers.
They are recording history.
Yes. They contain a permanent microscopic memory of every massive windstorm that ever pushed against them, every sudden, jarring braking of a heavy semi-truck, every microscopic thermal expansion from a blistering hot summer day, and every impact they have ever endured. Their internal crystals bear the microscopic scars, the strain hardening, and the fatigue of their entire history. They are shaped by what they have survived. So as you look at the architecture holding the roof above your head right now, ask yourself, what is the structure around you remembering?